In this video, we're going to discuss about sinusoidal signals and Fourier transforms. Basically, we will look at different representations of sinusoidal signals, and then we will be looking into Fourier transforms, and also we'll be looking into the motivation that how Fourier transforms are important. Okay, let's start with representing sinusoids or sinusoidal signals. You have a signal xt, a continuous time signal, which is a sinusoidal signal. So basically, in general form, I can write it as, okay, some amplitude a times sine 2 pi fct. So what is 2 pi fct? It's 2 pi, the frequency, and t is the time, continuous time. What is the time period of this signal? It is 1 upon fc. If I ask you to plot this signal, how will you do that? So if you know fc, you know that the time period of this sinusoid is capital T, which is equal to 1 upon fc, right? And this is your time axis, this is your xt, and this is your 0. Very simple. Now, this is the continuous time signal. Of course, you can have phase delay, you can add a phase delay phi, and correspondingly you can move this. Okay, now let's go to the discrete time sinusoids. If I sample this signal with a sampling rate fs, what will it become? So basically it means that I have this sinusoid, this is capital T, and I'm sampling this with fs. So my sampling time ts is 1 upon fs, right? And I will be taking equidistant samples. So this is ts, right? If this is 0. And what is ts? Ts is 1 upon fs. And what I will get as a sequence of numbers, this sequence will be, okay, something like this, right? So now how do I write it analytically? So I know xn is simply sine 2 pi fc. I replace t with n times ts, right? I replace t with n times ts. Basically, n can take discrete values. It could be anything from minus infinity to minus 1, 0, 1, and so on, right? So there is no limit on that. But n should take discrete values at intervals of ts. So that is what I have replaced. Small t is replaced with n upon fs because ts is 1 upon fs. So I can write this in this 2 pi fdn. So now if you compare these representations, they look similar, but this fd is related to fc with this constant fs. So fd is the discrete frequency of the sinusoid, where fd is given by fc upon fs, right? So it depends on both the continuous time frequency as well as the sampling rate. So I hope this is very clear now. Let's look at one example to make it more clearer. So let's see a sinusoidal signal with a time period of 5 seconds. What does that mean? It means I have a sinusoid signal, and I know this is given to be 5 seconds. 0. This is time in seconds. And this is my x of t. It's a continuous time signal, right? Next is write the expression for this xt. All of you know xt is simply, okay, I'm ignoring the amplitude part, a times sine of 2 pi fct. What is fc? fc is 1 upon the time period, tc, which is equal to 1 upon 5. Right, so that's what I have written here, 1 upon 5. Now sample this signal with a sampling rate fs equal to 0.5 hertz. So what will be the xn now? Okay, let's see first. If my fs is 0.5 hertz, this means my ts is equal to how much? 1 upon fs, which is equal to 1 upon 0.5, which means 2 seconds. So which means I am sampling this at 2 seconds. So let us say once here, 1, 2, 3, 4. Okay, so at 2 and at 4, I have to sample. So if I sample at 2, I get this value. If I sample at 4, I get this value. And then don't forget to sample at 0 as well. So I get this value. So I will be getting, and then further, okay, I'll be sampling at 6 also. So, but within one time period, this is something like this. Okay, so this is how I've sampled it in the figure, but now analytically, how the expression will look like. So my xn will be simply 2 pi by 5t. I replace t with n times ts, which is equal to n times, or n upon fs, which is n upon 0.5, or it is equal to 2n. Right? So this is the expression for this. So I think now sinusoids and sampling is very clear. Let's move on to the Fourier transforms. Okay, so to motivate the presence of Fourier transforms, that why they are or how they are very important, let us look at one very simple example. Let us say I have got a mixture of sinusoids. Instead of a single sinusoid, now I have got two sinusoids which are linearly added. So I have cos 2 pi 5t, cos 2 pi 10t. So what is the frequency of this? You know, this is fc is 5 hertz, and for this your fc is 10 hertz. Let me ask you a question. Is the overall signal periodic? So the time period of this is 1 upon 5 seconds, and the time period of this is 1 upon 10 seconds. Is the overall signal periodic? The answer is yes, because both of these are multiples of each other. So what is the time period then? So this is, let's say, one signal has a period of 1 upon 5, and the other one has a period of 1 upon 10, which is somewhere like here. Right? So the mixture will still be periodic with a time period of 1 upon 5. The overall time period is 1 upon 5 seconds. Okay, now let us see. Okay, if I have A0 and A1, means they are mixed with some coefficients, can I estimate those coefficients if I do not know the expression for it, but I am just given xt values? If I am given an xt, can I estimate the A0 and A1, right? I do not have explicitly the expression for this, but just the signal is given to me. Let us try this. So consider if I multiply xt with this signal, with this sinusoid or cosine signal, what will I get? So I get A0, so I expand xt because I'm deriving the formulation for A0 now. So this is equal to integration from 0 to capital T. Now, how did I arrive at this? This will be clear in a moment. A0 times cos 2 pi 5t and cos 2 pi 5t. So what is cos A, cos B? Okay, some trigonometry now. So 2 cos A cos B is equal to cos A plus B plus cos A minus B. Okay, so what is cos A plus B? This will be, okay, let's say 1 upon 2 here. Cos of A plus B is cos of 2 pi 10t, and plus cos A minus B, which is cos of 0, right? Plus A1 times cos 2 pi, so again A plus B is 15t, 2 pi 15t, and so 1 upon 2 here, there's a bracket here, and cos plus cos a minus b, so it is cos 2 pi 5t dt. And what is capital T here? You know that we derived that the period of the signal is 1 upon 5 seconds. So I'm integrating over one period. Okay, now what do we get? So if I integrate it, what is the integration over cos of 2 pi 10t? So you can do it, it will be sine of the thing, and then when you integrate over the limits, it will become 0, right? So this part will become 0. What will be this part? This part will be cos of 0 is always 1. So it becomes a naught by 2 times capital T. Right? And this part is again 0 because it's the integration over the whole period. This part will again be 0. So overall, what do I get? I get this is equal to a naught times t by 2 So basically what I have seen is that this expression, I do not need the explicit form of xt to compute this, right? If I know the signal xt and I know this signal which is induced by me, I can estimate the values of a naught. Similarly, if I multiply with cos 2 pi 10t, then the other signal will cancel out because a minus b will be 0 and cos of 0 is 1. So I can estimate a1. I can get the value of a1 out. So in this way, this is a useful expression. Let's see another general form. Okay, now we saw that xt can be represented as cos of 2 pi fct, but now I want to introduce the notion of complex numbers. So complex representation of sinusoids. So you know that you can write your cos of theta is equal to e to the power I theta plus e to the power minus I theta divided by 2, right? So I replace this cos with that form. So I get ak, okay, e to the power I theta plus e to the power minus I theta, because there is a negative sign also there. So I can extend my limits from k equal to, instead of saying 0 to infinity, I can make it minus infinity to plus infinity, right? And then this cos gets converted into e to the power I theta plus phi, that e to the power phi and ak can be absorbed and to make another ak tilde or ak dash, and we get this. So these two ak are not same, so maybe I can call it as ak tilde, and this is another ak which absorbs the phase also. So this is a representation for a sinusoid, a complex representation for a sinusoid, right? Now, let us say I am given a mixture of sinusoids. So basically this same representation. How do I estimate the coefficients ak? So given that this is a periodic signal with a time period of capital T, because you know all these k's are taking integral values, so the overall period will still be capital T, right? So this is a periodic signal with time period capital T. Okay, now to find AKs, I will use the same trick, multiply with the conjugate. So this thing becomes, if I multiply this, if I say xt multiplied by e to the power minus j 2 pi k upon capital T times t, and I have to integrate over the period 0 to capital T, then what will this value be? So this is equal to summation over k, all k minus infinity to plus infinity, ak, and then e to the power j 2 pi k t upon capital T. This was my xt into e to the power minus j 2 pi k upon capital T times small t, and okay, integrated over one time period 0 to capital T. So what does this become? So I can see this clearly cancels out and it becomes summation over k. Okay, I'm sorry, there is a overloading of notation here, so let me correct that. So this was k, I multiply this with some other k dash, this is k dash, right? This is summation over k, ak, e to the power j 2 pi k minus k dash t upon capital T, and then this is integrated from 0 to capital T dt. What is this value? If k is not equal to k dash, then this term will be some non-zero number, let us say n, and the integration will be equal to 0, right? Then this is equal to 0, or let us say this part will be equal to 0 if k is not equal to k dash. However, if k is equal to k dash, then this part will become 1 and integrated over 0 to capital T, so this part will become capital T, right? This means this will be 1 if k is k dash. Okay, so I can write it something. Let us say k is k dash, so this becomes equal to ak dash times capital T, right? So in this way, I have gotten the value of ak dash. So by changing the value of k dash, I can derive all the values of k. So this is to say that, okay, if I assume my xt is, okay, if it is a periodic signal, I can break it down into many periodic signals which are okay, so you have got when k is 0, then this term does not exist and this is just a constant value. But if k is 1, then this is a sinusoid with a frequency capital T. When k is 2, sinusoid with half the frequency, and when it is k is 3, then further it will be harmonics. So basically these are the harmonics of capital D. Okay, so that's the motivation, that you can split any periodic signal as a sum of sinusoids of that same period. Okay, so this gives rise to a concept called continuous time Fourier series. So if xt is periodic with time period equal to capital T, then I can decompose xt in terms of different sinusoids. So this is a complex representation. If xt is real signal, then of course this will be cos, because the positive and negative will cancel out, as you saw in the previous case. And then this is the way. And then how do you derive the value of each ak? So each ak, you multiply xt with the complex conjugate of this thing, and then integrate over the time period, and you get t ak, and so ak is just 1 upon t times. So this is how you derive the coefficients. Now this concept, which was there for periodic signals, can be extended to aperiodic signals also. But the motivation is to find a transform which is useful in that sense. Basically, which can decompose x into many sinusoids. Okay, So if xt is not periodic, I can find a transform in this way. So I have any signal xt, I multiply it with e to the power minus j omega t. Here this omega can take any real value, right? And I integrate from minus infinity to plus infinity. And where my original signal was, means it could be written as, so just remember you had seen AK. So just we have this, instead of AK discrete AKs, now we have continuous time function of x j omega, continuous in omega basically, and you multiply this with e to the power j omega t d omega, and so this is how this is called this is a Fourier transform. So this, your xt can be transformed into x of j omega. Right? A useful example in this regard will be, if my xt is a sinusoid, sine, let's say 2 pi fct or cos 2 pi fct, let's make it cos. So what I find is my x of j omega will be a delta function at fc, right? You can see this. You can see the exact form. That is not important, but my motivation is to tell you that this transform is very useful because it is based on sinusoids, and as you can see here, a sinusoid signal will be a delta function in the transform domain or the Fourier domain. So this gives rise to a motivation to also apply this kind of a transform to discrete time signals. So let's see that. So in the beginning we saw continuous time Fourier series. Basically you have a periodic xt, a periodic xt, and you transform it into AK coefficients, right? And then we saw at a non-periodic xt, and we transform it into x of j capital omega, and we see that this is a useful transformation. Now we want to extend the same idea to discrete time signals. Let us say I have an xn, or let us see, if I have an xn which is periodic, then if I apply a similar Fourier transform to x of n, I get x of k, which is again periodic. And if I apply it to a non-periodic x of n, then I get x of e to the power j omega, which is periodic, and it is continuous in omega, right? And here the omega belongs to real, here omega belongs to real. But you see there is periodicity, because as soon as your omega becomes 2 pi, it is equivalent to e to the power j into 0, right? There is a periodicity here. So essentially omega belongs to 0, 2 pi. Okay, you can make it close this side and open the other side. So this is how the Fourier transforms are defined. I think you have seen this part in your EE200 course. So I took this liberty to define this in the beginning. This will also give you a basic overview of what we are going to do in subsequent videos. So this was the motivation of going from Fourier series to Fourier transforms in continuous domain, and then extending the idea to discrete time, right? A very quick overview of how they look like. So let us say you have a periodic signal xt. Okay, some of you might feel this is a little bit not clear because this requires some background of E200. Don't worry, in this course subsequently we'll be seeing all these things, but the purpose of this slide is to give you an overview of what we are going to see in the subsequent videos. We have a continuous, let us say we have a continuous time signal like this, and I transform it into a Fourier domain, and the transform will be something like this. This is aperiodic, continuous, and aperiodic. So this will be continuous and aperiodic as well. There's a nice formula here that if your signal is continuous, okay, I start with C and continuous and discrete, periodic and aperiodic. If your signal is continuous, its Fourier transform will be aperiodic. If a signal is discrete, its Fourier transform will be periodic. If a signal is periodic, its Fourier transform will be discrete. And if a signal is aperiodic, its Fourier transform will be continuous. Okay, let us look at this signal. This is xt is a continuous signal, continuous in time, and aperiodic, continuous and aperiodic. The corresponding transform will be corresponding transform will be, since this is continuous, it has to be aperiodic. So okay, aperiodic, but then this is aperiodic, so this has to be continuous. So this is again continuous and aperiodic. Now let us look at the next signal. So if I make this periodic, if my xt is periodic, then the corresponding Fourier transform, which we saw as AK is discrete and aperiodic. The continuous becomes aperiodic and periodic becomes discrete. So we call this as, and this is equivalent to sampling in the Fourier domain. So sampling in one domain makes copies in the other domain. So sampling in one domain makes copies, means basically periodic copies in the other domain. That's what you see. You sampled here, so you got copies here. You made copies here, you got samples here, with the discrete samples here. Now let's look at, now if I sample in this domain, what do I get? I get copies in this domain. That's what you get. So your single thing has become many copies now. And similarly, if I look at, so let us say this is discrete, so this will be periodic, and this is periodic, so this will be discrete, right? And then let's look at another case when we don't have copies here, but it's just, okay, let's say this signal, if I sample it, so what do I get? I get copies of this. I get copies of this. This is the aperiodic signal, which is discrete. So discrete becomes periodic and aperiodic becomes continuous. That is why this is continuous and periodic. X of e to the power j omega. Yeah, in this part is little advanced for those of you who do not know much of Fourier transform before, but don't worry, just skip it. But for those of you who have already seen it in the past, this will be a nice refresher and overview of what we are going to see in the future. So thank you very much.